this video we're going to go over how to do linear interpolation. So we're going to use this formula and we're going to go through some examples. So find the specific heat capacity at 53 degrees for liquid water. So we have the temperature at 50 and the temperature at 55, and we have the specific heat capacities as well. So since we're looking for the specific heat capacity at 53 degrees, Y is the specific heat capacity at 53 degrees. So Y1, we can assume this is 1 and this is 2, right? Because we need those values for X and Y. So Y1 would be 4181 multiplied by X2. So if this is column Y and this is column X, X2, so 55 minus X. So X refers to the value, which is 53 in this case, because that's where we want our value of specific heat capacity. So 53 plus Y2, so 4182. Then we have X, so 53 minus X1, so 50. All divided by X2 minus X1, so 55 minus 50. So if we plug that all in, we have 4181 multiplied by 55 minus 53 plus 4182 multiplied by 53 minus 50. And that's all over 55 minus 50. So that gives us CP value of 4181.6. So that's the specific heat capacity at 53 degrees using linear interpolation with units. So if you move on to the next example, still using this equation, we have find the viscosity of the steam at 136 degrees. So we have the temperatures 130 and 140, and we have the viscosities at these temperatures. So since we're finding out the viscosity, we want to find out Y. So viscosity is the Y column and temperature is the X column. So you can assign at any one of them 1 and 2, but for simplicity, because we have X2 minus X1, we can work in positives. So we can assign the larger temperature as X2. So one way to think of how to do it is you can assign the columns as X or Y, and you assign the rows as 1 or 2. So now we can plug all of our values into the equation. So to work out the viscosity at 136 degrees, we have Y1, so 13.2 times 10 to the negative 6, multiplied by X2, so 140 minus 136, plus Y2, 13.57, 10 to the negative 6, multiplied by X minus X1, which is 130. Because we're lack on space, we can do 136 minus 130, which is 6. And that's all divided by X2 minus X1. X2 minus X1. 140 minus 130 is 10. If we put that in the calculator, you have 13.2, 10 to the negative 6, multiplied by 140 minus 136, plus 13.57 times 10 to the negative 6 multiplied by 6, and that's all over 10. So the viscosity of the steam at 136 degrees is 1.34 times 10 to the negative 6. And of course we're in SI, so we have Pascal seconds for viscosity. So we're still just going to use this equation and apply it to these next two examples. So find the enthalpy of the steam at 549.15 Kelvin. So Kelvin is just a different temperature unit to Celsius, but it still measures temperature. So because we want to find the enthalpy, because the enthalpy is the unknown, we assign that as the y column, and the other one is the x. So we assign this as 1 and assign this as 2. So using the equation before, we have y equals, using this equation, we have y equals y1, so 2, 7, 8, 8, 1, 2, 3, multiplied by x2 minus x, so x2 minus x, so 553.15 minus 549 plus 15, so that's 4, plus y2, so 2779, 1, 2, 3, multiplied by x minus x1, so we have x minus x1, 549.15 minus 543.15, which gives us 6. Then we divide by x2 minus x1, which is 10. Plug that all into our calculator. 2788 times 4 plus 2779 times 6 over 10. That gives us 27826. And of course this is in joules per kilogram for the enthalpy of steam at this temperature. For the last example, find the thermal conductivity of water at 283 degrees. So we want to find the thermal conductivity. Same again, we just label everything and then we fill in our formula. So we have y1, 574 times 10 to the negative 3, multiplied by x2 minus x, so 290 minus 283, plus y2 multiplied by x minus x1, so x minus x1, which is 3, all divided by x2 minus x1, which is 10. So plugging this all in, we get 574 10 to the negative 3, multiplied by 7, plus 558 10 to the negative 3, multiplied by 3, and that's all over 10. So we get 0.5692 as our thermal conductivity, and of course we can write it in standard form. And that's it.